Hello students, welcome back. Let us resume our discussion in section 1. I made a little bit of change here in 1.5 area formulae. So let's review area formulas for sectors in terms of radian measure and degree measure. So for radian measure, we can do it like this. Entire circumference is 2 pi r. But if you have just a sector, then we don't claim entire circumference. How much portion? Theta radian out of total 2 pi. That's the ratio you have to multiply and simplify. You get r theta. It's a bit easier to understand it this way rather than going directly to the definition of theta, defined as S over R, dimensionless quantity, those kind of business. And you can use exactly the same arguments to the area of the sector. The area of the entire disk is pi r squared. But of course, if I have just a sector, just a piece of pi, then I cannot claim everything. So I have to multiply my proportion, theta radian out of total 2 pi. And simplify, you get 1/2 r squared theta. It's a bit easier to understand this way. And exactly the same argument applies to degree measure. Let's see, how about the circumference? 2 pi r the same. And then what proportion do I have to multiply? My degree angle out of total 360 degrees. That's the ratio now. Previously theta over 2 pi. Now degree angle over 360 degrees. Same for the area. Entire circle will have pi r squared, but I have only a piece of that pi. So the degree angle divided by 360 degrees. So degree angle out of total 360 degrees. That's the ratio you have to multiply. So same argument applies there. And of course, these formulae here are for radian measure. Now let's go to triangles. Our old friend, the area of a triangle is 1/2 times base length times height. Well, yes, we have been using it for a long time, going way back to elementary school days, of course. Now, we have new formula here, 1/2 AB sine of theta. So A and B are two sides, and theta is the angle in between. Here's a visualization. One for acute triangle, which is a bit easier to understand. So the area is 1/2 AH. A is base area, base length, and h is the height. And if you multiply a times h, then you're going to get a rectangle, right? So you're going to get this kind of rectangle. Height is h, and then width is a. And then if you consider this green region versus this part, they're the same. If you compare this white region and that part, they're the same. So basically you're looking at half the area of this rectangle. Remember this? Anyway, that's how you get 1/2 AH. Now let's apply some trigonometry here. Look at this green right triangle here. So sine of theta is opposite over hypotenuse, h over b. So let's make a little bit bigger here. H over b sine of theta. So flip b to the other side. H is b sine of theta. So plug that in place of h here and simplify. That's how you're going to get this formula here. The area of a triangle given as 1/2 AB sine of theta. A and B are the sides, two sides. Theta is the angle in between. Now, what if you have an obtuse triangle? This one's a bit trickier, but the same argument applies. Here, height is h. That's a vertical. And then sine of theta is vertical over radius. And radius here is b. Consider this point here, angle in question is the origin. And don't pay attention to this a part. Consider a circle of radius b going through. Kind of like this. Let me go back to the drawing mode. So here, this is the center, And let's consider a circle of radius b going through like this, and then this is the origin here, and then we have an x-axis like this, and then we have a y-axis going like that vertically, and then down. Okay, we have the angle theta. It's an obtuse angle, okay, alright, going up to here. And then this point here, in terms of coordinate, what you get, x coordinate I don't know, I don't have to figure it out at this moment, but y coordinate is h, that's height, and radius is b, so sine is h over b, vertical over radius. And then of course another way to look at this is to look at this green right triangle and use trigonometry of acute angle. Let's get out of drawing mode. But then again, for that you have to know sine of theta is same as sine of pi minus theta, which is not really obvious. Anyway, sine of theta is h over b is true for obtuse angle as well. So flipping over the denominator, we get h is b sine of theta. Plug that in place of h, this area formula. Then we get the desired formula again for obtuse triangle as well. Let's see, for acute triangle, I believe everybody should be able to understand it, and given picture, everybody should be able to reproduce this proof. Obtuse, not everybody. If you're majoring in mathematics, alright, but otherwise, I'm not going to overemphasize that much. So okay, so much for the area formulas here. I made a bit of an adjustment from the previous notebook, previous lesson video, I mean. So I did it again here. Okay, let's go to the area problem here in 1.6. Here we go. Find out the area of this green region and red region here. The green region here is part of the circle of radius 4, and the center angle is 2 pi over 3 radian, which is 120 degrees. Now, if you look at the second picture, second circle is actually half the radius. So these are not drawn up to scale. So radius is 2, and the center angle here is pi over 3, 60 degrees. And of course, the other angle here is 5 pi over 3, of course. So how do you find out the area of this green region? Stop the playback and think about the strategy, and do the same thing for part B. Well, here's my strategy. Consider this entire sector. And then everything, entire sector. And then how do you get the area of the sector? Yeah, we have the radius 4 and center angle 2 pi over 3, so you can find out. And then here, subtract the area of the triangle here. Can we find out? Yeah, we can. We have two sides, 4 and another 4. They're the same. And then this angle in between, 2 pi over 3, so we can find out the area of the triangle. Subtract from the other, just like I just erased. And what's left is going to be the desired area. Does it make sense? So subtraction, sector minus triangle. Okay, how about the second problem? Think about that. If necessary, stop the playback. Any idea? Okay, here's my suggestion. Now let's do it this way. Okay, alright. First, let's consider the area of this sector with the angle like this. So basically, the majority part this part, area of this sector, which has center angle 5 pi over 3. So majority of this pi, or Pac-Man, if you remember old game, alright, and then add up the area of the triangle here. It's an equilateral triangle. Do you see? It's 60 degrees here and 2 and 2. So it's an equilateral triangle. So add up these two areas, blue, green, then you're going to get the area you want. So that's the second strategy. Excuse me, that's a strategy for the second problem. Alright, we just went through the strategy and how do you actually get it done. If you want to do some work on by yourself, then stop the playback and do some work there. Let's see if you did it right. And of course, if you think of some other methods, then you can use that too. Alright, here's the answer key for the first problem. What I'm going to do is find out the area of the big sector and subtract the area of the triangle, kind of like this. This one minus that one. Do you see that? This one here, we just follow the area formula of the sector, 1/2 r squared theta highlighted in green. And this one here, area formula for a triangle, 1/2 a times b, but a and b are both the same. And then sine of theta, the angle in between. So 1/2 4 squared 2 pi over 3 for the sector, and 1/2 4 squared and sine of 2 pi over 3. Do your computation and you're going to get this. 2 pi over 3 is a basic angle, so we get precise value. 16 pi over 3 minus 4 square root of 3. But if you punch in the calculator, you're going to get something like this. Alright, so much for the first problem. And the second problem, let's see, we get this kind of strategy. Get this sector plus that triangle. This one highlighted in red, this highlighted in blue, and then add them up. So 1/2 r squared theta, and that theta for sector is 5 pi over 3. So we have 1/2 2 squared 5 pi over 3. That's red Pac-Man. And how about this blue triangle? 1/2 a times b, but they're both same. 2 times 2, so 2 squared, and sine of pi over 3. So that's the area formula applied here. And then if you do your computation, 10 pi over 3 plus square root of 3. Again, pi over 3 is a basic angle, so you get precise value like this. But if you punch in the calculator, you're going to get something like this, 12 point something. Alright, so much for some area problems here. And I have some interesting area problems in not very much in Pearson MyMathLab, but I do have some interesting problems posted in Canvas. The first problem is going to be elementary, but second problem is going to be even harder than what you saw here. That's going to be a challenge. Good luck.